In this video, we're going to look at slack variables and duality. In particular, we're going to look at the simplex algorithm, and in this part one, we're only going to look at an introduction to the simplex algorithm. The algorithm proceeds in 3 steps. The first is that we know the solution lies at an extreme point. So we choose a feasible basis and compute the corresponding basic feasible solution. Without further knowledge, we begin at the point on the origin where all of the slack variables equal the right-hand side values of the various constraints. So if we look at this diagram, for example, we're going to pick point A, where all of the slack variables are equal to the right-hand side constraints, and the variables x1 and x2, for example, are 0. So that means any constraint we have, then we don't have any x1 or x2, so in order to meet the right-hand side of that constraint, we set the slack variables to equal that. So the procedure is that we start at A. Now, of course, if you knew something that the algorithm doesn't know, for example, if you knew that this was a better point, D, then you might start at D. But because we don't know that, we always start at A. So then the second step is to verify whether or not the basic feasible solution from step 1 is also optimal. If the answer is yes, we stop, and if not, we continue to step 3. So we select an adjacent extreme point, a new basic feasible solution, by changing the old feasible basis by only one column vector. So in other words, when we look at that, we go from A to either E or to B. We cannot jump to C or D because that would mean changing more than one column vector at a time. And then step 3 is, once we've got this new basic feasible solution, is we verify whether or not it is also optimal, and if it's yes, stop. If not, we continue again to step 3, and we continue that until we find the optimal solution, which in this case is shown by point C. So let's take an example where we have wheat and corn, and we're maximizing output. Let's say that this is measured in, say, tons, and we get $3 per ton of wheat and say $5 per ton of corn. So that's our revenue, and we want to maximize that. That's net revenue. Now we have a constraint that in order to grow a ton of wheat, we might require 2 acres, and to grow a ton of corn, we might require 4 acres. However, we also have a constraint of 16 acres, so we can't have more. And we have a labor constraint that says for each ton of wheat, we need 6 units of labor, and for each ton of corn, 3 units of labor, but we only have 18 units labor total. And we have our non-negativity constraint as before. So we introduce slack variables. So in the first equation, we call that slack variable x, S1, and in the second equation, the slack variable, we denote XS2. Notice that XS1 and XS2 enter the revenue function, but they have no value. So of course, they're not going to be picked in solving the problem. Again, we have this non-negativity constraint where XS1 and XS2 are also non-negative. So in the above, wheat and corn are measured in the same units. Thus, the amount of land needed to grow a unit of corn is greater than that needed per unit of wheat. In the final solution, a slack variable may be greater than 0. Since not all of the resources used, its shadow value is thus 0. And we saw that before, but this is the linear programming equivalent of what we had looked at earlier, the complementary slackness condition. And that says that the shadow value of the slack variable times the slack variable has to equal 0. So in other words, either the shadow value is 0, in which case even if we had more land available or more of that slack variable, then its value is 0, we don't use it. Or the shadow price might be greater than 0, in which case we've basically set the slack equal to 0, which means that we're using all of that resource. So to sum up, either there is no unused resource, xs equals 0, or its shadow value, denoted by this lambda, is 0, or both. Now this is the same as that Karush-Kuhn-Tucker condition that we found previously. So here, we start at step 1. We start with this feasible basic solution where x1 is 0, x2 is 0, and both of the slack variables are positive, they're greater than 0. We calculate the value of z, which in this case is 0 at that point. We look at an entry criterion. So we select the activity that's associated with the most positive coefficient in the objective function. So if we look at the most positive coefficient in the objective function, then we see that it's corn, x2. So we enter x2 into the bases. We shift the basic feasible solution from one extreme point to an adjacent one. Activity x2 enters the bases, so one of xs1 or xs2 must exit. Determining which to exit, which to get rid of, is a decision variable with economic meaning, and that's part of what we're going to be doing over the next little while. So again, in summary, we started with x1 equals 0, x2 equals 0. The slack for the land constraint was 16. The slack for the employment or hours work constraint was 18. We see that x1 remains 0 in the current one. So if we look back at this diagram, even though it's not quite applicable to our situation, we're moving in this, x1 remains 0, so we're moving in this direction. We'd be heading toward B. So the x2 enters, so we have xs1 equals 16 minus 4x2, and xs2 equals 18 minus 3x2. So we have to solve these equations. So x2 here turns out to be 4, so the most x2 that we can enter based on the first constraint is 4 units. Based on the second constraint, it's 6 units, 18 divided by 3. But this is the constraint that binds. So all we could do is enter 4 units. So we use this minimum ratio criterion, where x2 is the minimum of 16 over 4 or 18 of 3, so 4 or 6, and it's equal to 4. Therefore, the new basic feasible solution is x1, 0, x2, 4, xs1, 0, but xs2 remains at 6. The exit criterion, to change the current feasible basis, eliminate the column corresponding to the index in the numerator of the minimum ratio. So the x new is the minimum of the value of the current feasible solution divided by the positive coefficients of the new activity. So take xs1 out of the basis and replace it with x2 is our result. So now, iteration 2, step 2. Evaluate the current basic feasible solution. So we have 4 units of x2 times 5 is 20. 3x1, x1 remains 0, so that's 0, and these have 0 value, so the value of z is 20. Corn is in the bases. All land is used up. That's a key. All land is used up, but there is slack labor. Remaining candidate to enter is wheat, but to get wheat in, some corn acreage must be given up. So we must determine the opportunity cost of wheat in terms of corn. So do you understand? This is key here. All right. All land is used up, but there remains slack labor. And the question is, if we can shift from x2, where we have 4 units, to x3 by using some of that slack labor, we can convert some of that corn acreage into wheat. So we want to determine whether that's economically feasible. Now we recall this total derivative, which we've had numerous times already by now, where the dy equals the marginal product of x1 times dx1 plus the marginal product of x2 times dx2. That's basically our production frontier when we set dy equals 0. Here we're dealing with a z, of course, but that's kind of the idea. So we have that f1 dx1 plus f2 dx2 equals 0, which is the marginal rate of transformation, technical transformation from x2 to x1. From x2, all right, from x2, which is 4, to x1, which is currently 0. And that's equal to the minus dx2 over dx1, which is the marginal product of 1 divided by the marginal product of 2. So this is the slope of that trade-off curve, and this is also the negative of the slope. So it's the marginal sacrifice. Look at here, this dx2 is the sacrifice that we make if we switch x2 into x1, and so it's the marginal sacrifice of f1 over the marginal sacrifice of 2 that we're interested in. This is the marginal sacrifice f1, this is the marginal sacrifice x2. So the constraint on land is 2x1 plus 4x2 plus this slack, which is equal to 16. Total differentiating, we get 2dx1 plus 4dx2 equal to 0, as this xs1 is taken as a constant. So the marginal rate of technical transformation of x2 into x1 is minus dx2 over dx1, which we see when we solve this is equal to 1/2. So we move this, move that over to that side. We get a negative 2 divided by 4 is 1/2, and we're taking the negative of it, of course. So a generalized matrix version of this is we maximize C of x subject to ax1 plus bx2. The marginal rate of technical transformation from x2 to x1 is given by minus dx2 over dx1 when that total derivative that we calculated up here, okay, right here, when that's equal to 0, and we get b, the inverse of b times the a. And this is if we have matrices or vectors, all right, and which we do in this case. So recall our problem again, that wheat and corn output optimization. We get 3x1, 5x2 is the revenue, and we have that like that. So what's the opportunity marginal cost? The sacrifice of one additional unit of output as measured by the foregone alternative production opportunity, which is measured by the marginal rate of technical transformation, or the slope of the transformation frontier. Transformation frontier can be thought of as our production possibility frontier. A sacrifice can be positive or negative. We want to avoid a positive sacrifice and welcome negative ones. So when we give up our land in corn and put it into wheat, we want to make sure that we don't sacrifice, that sacrifice is not positive, but that it's negative. So the opportunity cost of wheat is equal to the sacrifice in terms of corn minus the unit revenue of wheat, which is equal to the wheat land divided by corn land times the revenue of 1 unit of corn land minus the revenue of 1 unit of wheat land. So what we're saying is we're going to take wheat land divided by corn land, multiply it by the revenue of 1 unit of corn land. So that's the revenue, that's the sacrifice, minus the revenue of 1 unit of wheat land. So it's 2/4, that's wheat land over corn land, times 5, which is the revenue of 1 unit of corn, minus 3. and that turns out to be minus 1/2. Because it's a negative sacrifice, we do want to take some of that corn land, put it into wheat, take that free labor, if you like, because it's excess labor, and use it to produce wheat by taking excess labor and any freed up labor from corn. So the marginal rate of technical transformation, we find wheat land to corn land is equal to wheat land over corn land is 2/4. Note that the marginal rate of technical transformation is constant, which is why it is simply a ratio, and that's because of the linear programming assumption. Everything is linear. To improve returns, therefore, we redistribute available resources from corn to wheat production. Since the sacrifice is negative, there is a benefit from doing so, from giving up corn, as the opportunity cost of wheat is less than 0. So in step 3, we showed wheat enters, what activity should leave. While the opportunity input requirement of a given commodity, wheat, is the savings, as opposed to the sacrifice, of inputs attributable to 1 unit of foregone activity, corn, adjusted by that marginal rate of technical transformation. Recall, the land constraint is fully satisfied, which is why we have to look at that. So we're looking at the opportunity labor requirement of wheat, which is equal to wheat labor requirement minus any savings in terms of corn. So if we had, if wheat required 5 units, let's say, and the savings in corn was whatever it is, then as long as that's positive, we're better off. So what we had was a wheat labor requirement. We saved 6, or we need 6 units of that, but we saved 3 by moving some of the corn land into wheat and shifting the labor from corn into wheat, which is what this is telling us. All right, so the 1/2 was that marginal rate of technical transformation from going from corn to wheat in the land constraint, since the land was limiting, and this is then the labor saving when we move that much corn out of corn land out of taking corn land and shifting it into wheat. Okay, and that's as far as we're going to get in this particular video. We'll look at it from a different perspective in the next video. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.